Hi, welcome back. It's my pleasure to introduce Dr. Shilin. He's currently a senior researcher in Microsoft. His research focuses on AI ops, log analysis, large language models, and etc. More specifically, he aims to apply machine learning or deep learning techniques into management and maintenance of cloud systems. Shilin has published many papers in top-tier venues such as ICSE, FSC, ASC, CSUR, ICLR, EMNLP. He received ISRI 30 years most influential paper award, FSC 2022 Distinguished Paper Award. He is the PG member of ISTA 2024 Research Track and FSC 2024 IVR Track. According to Google Scholar, his papers received about 2,400 citations. His work has been integrated into many Microsoft products such as Azure, M365, and Bing. He joined Microsoft in 2020, shortly after he received his PhD degree from Chinese University of Hong Kong. Welcome, Shilin. He is going to talk about this distinguished paper award winning topic on scalable log parser with feedback guidance. Shilin, over to you.
Okay, thank you. Thanks for the introduction. Hello, everyone. My name is Shilin He. I'm a researcher from Microsoft. Before the talk, I would like to say a big thank you to Professor Sujit and all conference organizers for inviting me and hosting me. I'm so sorry that I cannot attend the conference in person due to the visa issue. So in this talk, I will introduce our recent work, SPINE, a scalable log parser with feedback guidance. This paper was awarded with Distinguished Paper Award on FSC 2022. I'm so glad to share with you this paper and have further discussions. So before deep dive into the technical details, I want to introduce some background knowledge about logs. Log, together with the metric and trace, are called the three pillars of observability. That means with these three types of data, people can better observe the running status of software systems. The observability is very important to today's IT industry, where the software has become super complex. And our work specifically focuses on logs, which record important system events and runtime status, usually in text. The log data provides the first-hand information to developers and operators. And the right figure is an example of logs from the Hadoop distributed system. And the natural question is, how is log data produced? As shown in the following figure, developers first write some logging statements code during the software development phase. Then when the software is running and that line of code is executed, and the log will be generated accordingly, together with some meta information such as the data time, component name, and the verbosity level, etc. Log can be categorized into various types, such as the system logs, like the Windows event, application logs, database logs, network logs, and many more. The logs play an important role in many scenarios. For example, when debugging and troubleshooting some software issues, you need to check the logs to get more information. And you can also gain valuable insights by analyzing the user behavior logs and support the business decision making. And other typical scenarios include monitoring performance, analyzing security issues, etc. However, the rapid increase of log data volume and complicated dependency among different log events pose a great challenge to manual log analysis. Therefore, many research efforts in the automated log analysis have sprung up in recent years, such as the log-based anomaly detection, log-based failure diagnosis, failure prediction, and log compression. And a general workflow of the log data analysis is shown in the figure below. The log data is usually collected first and then passed into a structured format. Next, we can extract features and perform some downstreaming tasks, such as the anomaly detection, as mentioned earlier. And as you may observe, log parsing here is the second step. It is actually very critical in this entire workflow. Formally, log parsing is defined as extracting log templates and log parameters from the raw log messages. In this figure, a log message usually contains a fixed header, including the information such as the timestamp, the component name, the velocity level, and the log message body typically consists of two parts. One is the log template, the static keywords describing the system events, which are often explicitly written in the logging statement code. And another part is the log parameters, the dynamic variables that keep changing during the runtime. And here our goal is to distinguish the two parts and extract the structured format from the raw unstructured log messages, or we call it log parsing. And actually, in the past few years, many log parsers have been proposed and achieved promising accuracy on public log data sets. But they still face many challenges in real-world applications. The reason is that there is a huge gap between the industrial log data and the public benchmarks. Therefore, we first conducted an empirical study on the industrial logs to reveal the characteristics of the real-world log data. Firstly, industrial logs feature extremely large scale. For example, we studied logs from an online service system in Microsoft and found that there are more above 5 billion log messages generated every day, which means about 200 million logs per hour. In addition, we found that the log data is often extremely imbalanced. The center figure shows that the histogram of the number of logs with different templates, and the x-axis denotes the template ID, and the y-axis denotes the number of logs for each template. And we can see that the logs are dominated by a few log templates. In fact, the top 10 log templates account for about 75% of total logs. So that's why we call it the data imbalance issue. And thirdly, new log templates will emerge continuously in production. In production service system, we count the number of new log templates in each week, as shown in the right figure. And we can find that the number of log templates continuously increase compared to that of the first week, which means the starting point here, due to the continued integration and delivery paradigm of today's software development. So considering these real-world challenges, we try to summarize the basic requirements for an ideal log parser that can be widely adopted in practice. First is the accuracy. There is no doubt that the parsing accuracy is always the most important metric for a log parser. And secondly, the log parser is required to be scalable. As earlier mentioned, the log volume in practice is very huge. So standalone log parser, like most existing work, do not flexibly scale up by design and cannot satisfy the industrial needs. And finally, the log parser should have the ability to evolve to fit the new logs and allow the end users to fine-tune the parser with some minor feedback. So to meet these demands, we propose Spine, a highly scalable log parser with feedback guidance. And here is the overview of Spine. It has two phases, the offline training, the top part, and the online parsing, the bottom part. And in the offline training phase, Spine trains a model based on the log data collected so far, which will later be used in the online phase online parsing phase. And specifically, spine consists of 4 components, that is the pre-processing, initial grouping, progressive clustering, and the online parsing. And the high-level idea for the training phase is to group the logs into many clusters from a coarse-grained to fine-grained fashion. And in this way, similar logs will appear in the same group, and we can then extract the log template accordingly. And in the online parsing phase, Spine directly applies the length model to newly arrival logs and finds the best matching template for each log message. And next, I will explain how each component works. In the pre-processing stage, we will first tokenize the log message. That means we will split each log message or the log sentence into a series of tokens by delimiters like space, column, bracket. Next, some cleanup efforts are necessary. For example, we can remove some commonly used parameters, such as the IP address, the query ID, bypass, so on and so forth. And with these steps, the logs will be much easier to parse. After the pre-processing, initial grouping is used to cluster similar logs in a coarse-grained fashion. That is, we will group the logs into some large cluster or large groups. And the goal of this step are twofold. Firstly, because in the next step, we will apply a clustering algorithm, and it will be much faster to cluster a small number of logs comparing to a huge number of logs. So that's why we need to reduce the log volume by something like the divide and conquer concept. And secondly, by partitioning the data into multiple groups, the parallelization becomes possible. It requires us to split the logs into disjoint log groups. So specifically, we observed that the log messages with identical first key tokens belong to the same log group because they are more likely to share the same log template. So we use it to do the initial grouping. For example, here are some logs, and if we just split them according to the first token in each log message, then we will have 3 different groups that are mutually exclusive. And we may also consider other log properties, such as the log length, component name, and verbosity level to do the initial grouping. So far, the log messages have been roughly grouped into some large log groups, but that is not the end. Logs in one log group are likely to have multiple log templates, and we need to further divide the logs into more fine-grained log clusters for template extraction. So in Spine, we adopt a progressive clustering algorithm. It iteratively partitions the log messages into 2 subgroups. Ideally, if we do not add any restriction to this process, the clustering will not stop until each cluster only contains 1 log message. But that is not what we want. So we designed a stop criterion to guide the algorithm to stop this kind of iteration. And at last, you can obtain a binary clustering tree as shown in the right figure. And the leaf node are the log clusters that we want. So as shown in this figure, for example, after the initial grouping, we have a large log group here. And in each iteration, we will split the group into 2 clusters. That means 2 nodes here. And we will continue to expand this binary tree until the stop criterion is satisfied. That's the overall idea. So in this process, you may find that the design of stop criterion is very important. And we call it the token saturation rate in the spine. So before the concept introduction, I will first introduce the saturation tokens. Actually, the saturation tokens are defined as tokens that appear in every log message in a group. In this example, the tokens in the red color are saturated tokens because, for example, here the task appear in every log message in this group. And then the token saturation rate of one log message is defined as the ratio of saturation tokens over all tokens size in this log message. And we will use the average token saturation to guide our progressive clustering process. And the intuition is that a cluster of logs from the same log templates should share many common tokens, which means more saturated tokens. So with this criterion, log parsing granularity can be well controlled. And after clustering the logs in a leaf node here, they are likely to share the same log template, and the saturated tokens can then be directly extracted as part of the log templates, while other tokens can be naturally treated as the parameters. And we will save this tree and also the templates from each leaf node as the model for the later online parsing phase. Okay, then in the online parsing, each newly arrived log within the current batch will first be preprocessed and assigned to an initial group according to its first K tokens. Next, based on the templates extracted offline, we will try to assign the log, for example here the log, to the most similar log templates by calculating their textual similarity. And so far, we have introduced the building blocks of Spine for offline training and online parsing. Next, we will highlight two advanced features, that is, how to achieve log parsing in parallel and how to incorporate user feedback. So as mentioned earlier, log groups generated by the initial grouping are mutually exclusive. So logs in different groups can be naturally processed in parallel during the online parsing. It seems that we need to do nothing because the parallelization is very natural. But unfortunately, due to the imbalance issue we introduced earlier, the size of one log group can be several order of magnitude larger than another log group. Consequently, the parsing time of some log groups can be significantly longer, and the overall parsing time will be determined by the largest log group. So to address this issue, we propose a log data scheduling approach. The core idea is to split some large log groups into smaller groups and assign to multiple executors for parsing. Meanwhile, some small log groups will be merged for parsing by one executor. So in this way, the workload of different executors tends to be balanced. And here the executor can be a single process or even a physical machine. And the algorithm is presented in the right part. We first sort all log groups according to their size in descending order. Then we split the log groups whose size are above the average, which is calculated based on the number of logs to be scheduled and the number of available executors. Those large groups will be split uniformly into several subsets, and each subset has the log size close to the average and will be assigned to an executor. And after all above the average log groups are scheduled, we leverage the best fit algorithm to pack all subsequent log groups into supersets and assign them to the rest of executors. As for incorporating the user feedback, it happens during the progressive clustering. The core problem is how to leverage user feedback to decide whether a leaf node should be split into two child node or not. The feedback process involves multiple rounds of user query. As shown in the right figure, in each round, Spine will recommend a pair of logs from the same log cluster. Then the user gives feedback about whether this pair of logs share the same template. This feedback process continues until the interaction rounds have reached the limit specified by the user, or there are no more log clusters worthy of querying feedback. And since the query budget is often limited, how to recommend the most valuable log pairs for user feedback? So we designed a metric named the saturation gain, which is the increase of saturation if we split a leaf node into two child leaf nodes. And a higher saturation gain denotes that splitting the current leaf nodes is beneficial to improve the overall parsing accuracy, and it is worthy querying the user feedback. And we conducted extensive experiments on 16 public benchmark datasets from the logPy benchmark. And the logPy is currently one of the most famous log datasets for intelligent log analysis. And in our evaluation, we follow a widely adopted metric named the parsing accuracy. The parsing accuracy is defined as the ratio of correctly parsed log messages over the total number of log messages. And we compare Spine with 5 state-of-the-art log parsers, that is the AL, Lemma, Spell, IPLOM, and Drain. We implemented several versions of our proposed log parser: Spine Base, Spine Feedback, and Spine Parallel. Spine Base is the basic version of Spine without parallelization and feedback guidance. And Spine Feedback adds the feedback guidance on top of the Spine Base. Spine Parallel, it is the parallel implementation of the Spine equipped with the log data scheduling algorithm. For the parsing accuracy, the experimental results are shown in the table. From the table, we can see that Spine outperforms the 5 baseline methods on most log data sets. So here, each row is a log data set, and each column is the method. And the number here denotes the parsing accuracy. And the last column is the best accuracy among all the 5 baselines and our proposed Spine method. So for example, even though we combine with the most powerful parser Drain here, Spine still achieves better results on 8 datasets and achieves comparable accuracy on 5 datasets. And to measure the efficiency, we compared the execution time of Spine with the baseline log parsers on 3 log datasets. From the figure, we can conclude that the Spine base, which is denoted in the brown line, it outperforms all existing log parsers, especially when the data size is large. So as you can see, we will get a slightly larger gap with the when comparing with the baseline log parser in the execution time. And also the execution time increased linearly with the size of logs on this data set. So for example, in the HDFS data, the log data set, the Spine base only spent about 4 minutes to parse 10 million of log data. And we also evaluated the effectiveness of Spine Parallel on 3 data sets, including the HDFS, the BGL, and the Spark. So here the HDFS comes from the Hadoop distributed file system. BGL comes from a supercomputer system, and Spark is the one for data analysis, large data analysis. So in order to simulate the log volume in the real world, we expand all 3 data sets to 30 million with uniform replication from the original log data set. And we run the spine parallel with different number of executors, and we call the execution time for each data set. And the results show that our proposed log data scheduling method can significantly improve the parsing efficiency. And more specifically, the spine parallel here, it can achieve about 5 times more throughput improvement for the BGL data set with 16 executors. That is about 200,000 logs per second. You can process it. Moreover, we compared the spine parallel with a naive best fit scheduling approach, where large log groups are not split into smaller subsets. This kind of baseline method is denoted in the orange line, and it can be observed that our method achieves a higher speed up ratio with more executors. For example, those executors greater than 16. And when the number of executors is fewer of that of log groups, our method will degrade to the best fit scheduling algorithm, because all the log groups can be directly packed into a few supersets with similar size. So that's why from the figure, we can find that the two scheduling methods achieve similar performance with 1, 4, and 8 executors. And we also applied the spine feedback on the 3 data sets with unsatisfactory parsing accuracy. That is the Linux, Mac, and OpenStack logs. The only unsatisfactory parsing accuracy means that all log parsers, including the baselines and our methods, cannot achieve good results on the 3 data sets. And to conduct this experiment, we first train an initial parsing model for each data set, and then query the user feedback for the log clusters with the highest saturation gain score, which is exactly as same as what I mentioned earlier. And we also implemented 2 additional log selection strategy as the baseline. The first baseline is the random state strategy, where a pair of logs are sampled randomly for user labeling. And the second baseline considers the leaf node size to make the recommendation. That means here we believe the leaf node with a huge number of log data should be divided into more clusters. That's why we will recommend logs from that cluster. And we can confirm that all 3 strategies can improve the parsing accuracy with more user feedback provided, as shown in the 3 figures, because we can all see that with the increase of number of feedback queries, the parsing accuracy will also increase. But we can also observe that our saturation gain-based method achieved the highest accuracy compared to the other 2 baselines. For example, the parsing accuracy can be improved to above 0.9 in less than 10 iterations for the Linux and also the OpenStack log data sets. And even for the Mac log data, which is more difficult, the parsing accuracy can be optimized from 0.78 to more than 0.85 with 20 iterations. Besides the public benchmark, we also applied spine into log processing pipeline for Service X in Microsoft, and we recommend log pairs to engineers and collect the feedback from them every month. The blue curve in the right figure shows the parsing accuracy declines with time if we do not include any feedback guidance, while the orange curve here shows the parsing accuracy with user feedback. And note that we did not provide the user feedback every week. Instead, we add some user feedback every month. So since the first week, the next feedback time is about the 5th week, and the next is the 9th week. Yeah, that's how that's when the engineering feedback are provided. And we can see that there is a significant parsing accuracy boost after querying the user feedback in the week 5 and week 9. And in addition, we run spine with 16 executors to pass the log data from service X. Here, the 16 executors are actually 16 processes on a physical machine. And we show the log volume of every 2-hour time window and the time cost for the log parsing in the right figure. So why the 2-hour time window? That is because actually this service, we have another monitoring pipeline that are built on top of the parsing results. And it requires the parsing of each time window should be finished in 10 minutes. So as you can see here, for every 2-hour time window of log data, we need to finish it within 10 minutes. And successfully, we find that on average, the spine only spend about 8 minutes to pass 30 million logs, which fulfills the requirements of the Service X. So in summary, we propose the spine. It's a highly scalable log parser with feedback guidance. And in detail, we proposed a novel log data scheduling algorithm to improve the efficiency on large scale and imbalanced log data. And in addition, we incorporate the user feedback to support the evolving log data. And the experiment results confirm the effectiveness and also the efficiency on both public and the production logs. And considering the future directions, I just list 2 potential directions for sharing. The first is the log LLMs at log parser. Here we know that the LLMs are really very popular in recent year, or specifically in the last year. So we can directly apply the LLM as the log parser. But there are 2 questions. One is how to achieve the higher parsing accuracy with better prompt engineering. And here you can see this is an example. I just tell the ChatGPT to pass the following logs into templates, and it can output the correct result here. Start executing the job with the job name. And but here the question is how to get a better prompt engineering to better guide the LLM to perform. Do we need to include some, for example, some log parsing demonstrations to improve the performance? And the second core question here is how to deal with the efficiency issue, because the LLMs are pretty slow in handling the data. So if we have, for example, 1 million log data to process, we cannot afford it. Not only the time, but also the cost, the money cost. Yeah. So how to deal with the efficiency issue is the second challenge. And another direction is based on the counter spine framework. We may also incorporate the LLMs as the feedback provider. As I mentioned earlier, currently we use the human as the feedback provider to guide the spine to better perform on the evolving data. But with LLMs, because its capability is very similar to human, so can we leverage it as the feedback provider So we can naturally incorporate it with the spine framework. And also we do not need to worry about the cost and the time, because the spine itself is very effective and efficient enough. Yeah, I think that's two future directions that we may consider in yeah. Okay, I think that's all for this sharing. So any questions from the audience?
Any questions?
I had a question. I really enjoyed your talk. The question was, what happens when there is a parsing inaccuracy? Like, is there a, what effect does it have, and how does the user recover from that? Thanks.
Okay. Let me repeat question. Are you saying what is the how to say it? Why do you met the login the parsing accuracy, right?
I was asking if log is incorrectly classified, what's the effect of that in the real life situation?
Okay. So you I understand your question. So you are asking the consequence of wrongly passed logs.
Yeah.
Okay. So actually, as I let me switch back to the previous slides. Yeah, as you can see here, the log parsing is the second step in the entire intelligent log analysis workflow. So once the log parsing is inaccurate, it will affect the feature extraction and also the downstream task. For example, the anomaly detection. So previously we have a paper studying this kind of effect. The log parsing accuracy decrease about the 0.2, the anomaly detection will drop a lot. So that's the consequence of the log parsing. And also in the online system, if the parsing accuracy is very low, it will affect the monitoring of the system. That means you might miss some logs that are critical because you only categorized it into another log template. So that's what we cannot afford. So I think, does it answer your question?
Yes. Yes, thank you.
Okay, thank you.
I had another question. So there was some work by David Walker, etc., like more than Kathleen.
Sorry, I think the microphone is not very clear. Can you repeat it?
There was some. Can you hear now?
Yeah.
There was some work by David Walker and Kathleen Fisher in the PADS project. More than 10 years back, I think. Yeah. So they were also dealing with parsing of log messages, and yeah, I think log messages particularly, and they had a data description language for log messages. They could infer the data description language and do efficient parsing and all that. Could you are you aware of that work, and could you comment?
Actually, I just missed the work you mentioned. Can you say it again? Because I think the mouse is too close to the microphone, and I cannot hear it very clearly.
It's the PADS project, PADS project.
PADS. Oh, sorry, I don't know it. Yeah, go ahead.
Okay, thanks.
I have one question. I mean, maybe you explained it, but do you do causal analysis of messages?
Causal analysis for log messages, right? I think that is out of scope of the parsing, but there are some research studies on how to analyze the log for the downstreaming tasks. So one typical example is for the anomaly detection. That means in their scenario, the input is a number of log data, and people try to recover the causal dependency among these log messages. The causal dependency actually means the execution order from the source code or different components in a large software systems. So when some failures happen in a software system, it's high likely that the order between different messages between different log messages will be masked. So that's how people leveraging, for example, causal analysis or other dependency mining techniques to identify the anomalous log sequences.
So if you have two logs generated at two different times, I mean, are we able to compare them through this?
Two logs generated in two different times, and then
You have to compare them. Comparison between those logs. So because this data will be large, right? I mean, every day you might get a bunch of logs, you might get list plots, but how you do the trend analysis of over the period, how they are evolving?
Can you compare? I mean, that's the question. Can you compare two logs using your framework?
Okay. Actually, here we did not see much value of directly comparing two log messages without parsing. Instead, we think we can compare the logs after the parsing, because after that, the logs will become the log template, and this template just mean a meaningful event in the software execution. So comparing that would be much more meaningful. I'm not sure whether this answers your question.
It answers. Thank you. Yeah, it
Okay,
answers.
thank you.
Yeah, one more question.
Yeah, thanks for a good talk. I'm Girish here. Is this work likely to be incorporated in your log P AI open source project that you are maintaining?
Well, okay. Thank you for the question. Yeah, actually, the LogPy project, I was involved in that project during my PhD study, and later the spine work is conducted when I'm in the Microsoft. So currently there are some the IP issue. So it's more likely if we open source it, it will be a separate repo instead of incorporating in the current LogPy repository. So we are still trying to figure out how to do this.
Okay, any other questions? Yeah.
Hi, thank you so much for this talk. I had a question. So the log data that comes in is actually coming like a stream of logs, right? So how were you able to deterministically classify, or deterministically group this? Did you have some sort of a pattern matching that you said, and you kept refining your sets subsequently before the passing step?
Before the passing step, you mean find the pattern before passing step?
So typically industrial logs are high volume, right? And there's a potential for being unstructured. So
Yes.
How did you manage? Was it a time window based? So basically, I think I'm asking a question about the log collection step.
Okay. So actually, because we know the log data, they are collected in a streaming way. So each time, so when we develop the software, we will use some logging framework, and the logging framework will automatically collect the log data based on an agent on your host machine, and that data will be, for example, dumped into a database. And because we have the timestamp here, so we can use the timestamp as the key to group different log messages.
Okay, any other questions? Okay, there are no questions. Let's thanks the speaker. Thanks, Shilin.